Have you ever looked up at the stars and wondered, where did it all begin? Not just the universe, but us, life. How did a barren, rocky planet like Earth suddenly burst forth with living things? It's one of the biggest, most profound questions humanity has ever asked. And the truth is, despite all our science, all our technology, and all our brilliant minds, we still don't have a definitive answer. It's a mystery that continues to captivate and puzzle us. Let's rewind the clock, way back. About 4.5 billion years ago, our solar system was just forming, and Earth was a hot, chaotic, and completely lifeless place. It was constantly bombarded by asteroids and comets, its surface a molten sea of lava. Not exactly a welcoming home. But fast forward a few 100 million years, and something incredible happened. The planet cooled, oceans formed, and against all odds, the first simple life forms emerged. The big question is, how? One of the most popular ideas, the one many of us learned in school, is the primordial soup theory. Picture this. Earth's early oceans were a warm, shallow broth, a chemical cocktail filled with simple organic molecules. These molecules, energized by lightning strikes and intense ultraviolet radiation from the sun, started linking together, forming more complex structures like amino acids and nucleotides, the very building blocks of life. Over millions of years, these molecules organized themselves into the first self-replicating cells. It's a beautiful and elegant idea, first proposed in the 1920s. Scientists have even recreated these conditions in the lab, showing that simple organic compounds can indeed form from inorganic materials. But there's a problem. Creating the building blocks is one thing. Getting them to assemble into a living, reproducing cell is a whole different ballgame. It's like having a pile of bricks, wood, and nails, and expecting a house to build itself. The jump from a soup of chemicals to a structured, functioning cell is enormous, and we haven't figured out how that leap was made. So, if not a shallow pond, then where? Some scientists have turned their attention to the deep, dark abyss of the ocean. Down there, far from the sun's rays, are hydrothermal vents. These are like underwater geysers, spewing out superheated mineral-rich water from the Earth's crust. It sounds like an extreme and hostile environment, but these vents are teeming with life today. They create a unique chemical environment, a steep gradient of temperature and chemicals, which could have provided the perfect energy source and a protected cradle for life to begin. The idea is that these vents acted as natural chemical reactors, concentrating molecules and catalyzing the reactions needed to form the first cells. This deep-sea vent hypothesis solves some of the problems of the primordial soup theory. For instance, the deep ocean would have protected fragile, emerging life from the harsh UV radiation and constant meteorite impacts on the surface. It provides a constant, reliable source of energy and chemical ingredients. But again, while it's a compelling location, the specific chemical steps that would lead from vent minerals to a living cell are still largely theoretical. We haven't found the smoking gun. Let's move from the depths of the ocean to solid ground. Another fascinating idea is that life didn't start in the water at all, but on the surface of minerals, specifically clay. Clay has a remarkable property. It's made of layers of silicate sheets that can attract and hold on to organic molecules. Think of it as a natural scaffolding. This theory suggests that clay surfaces acted as concentration templates, organizing the building blocks of life into precise patterns. This structure could have encouraged them to link up into long chains, like proteins and RNA. Clay can also store and transfer energy from chemical reactions, potentially powering these early life-forming processes. It's a very neat idea, turning a simple patch of mud into the stage for life's grand opening. But like the other theories, demonstrating this process in a way that leads all the way to a self-replicating system has proven incredibly difficult. So we've looked at the ocean, the deep sea, and clay. But what if the key ingredient for life wasn't from Earth at all? What if it came from outer space? This is the idea behind a theory called panspermia. It sounds like science fiction, but it has some serious scientific backing. Panspermia suggests that life, or at least its essential building blocks, exists throughout the universe and is spread by meteoroids, asteroids, and comets. We know for a fact that some meteorites that have landed on Earth contain complex organic molecules, including amino acids and nucleobases, the letters of the genetic alphabet. There are different flavors of this theory. Lithopanspermia suggests that microbes trapped in rocks were blasted off a life-bearing planet by an impact and traveled through space to seed another world. Like Earth, it's a tough journey. They'd have to survive the vacuum of space, intense radiation, and the fiery entry into a new atmosphere. But we know some microbes are incredibly resilient. Another version, molecular panspermia, is a bit less dramatic. It doesn't propose that fully formed life arrived, but rather that comets and asteroids delivered the complex organic precursor molecules that were needed to kickstart life here on Earth. This would mean that the primordial soup wasn't just made of homegrown ingredients, but was seasoned with extraterrestrial flavor. This theory doesn't solve the ultimate origin of life, of course. It just pushes the problem to another time and place. If life started elsewhere, how did it start there? It moves the goalposts, but it's still a tantalizing possibility that connects our own existence to the wider cosmos. One of the central debates in the origin of life is what came first, the instructions or the factory. In modern cells, DNA holds the genetic instructions, the blueprint. Proteins act as the factory workers, carrying out all the functions of the cell. But you can't have one without the other. DNA needs proteins to replicate, and proteins need DNA to be built. It's a classic chicken and egg problem. This is where a very compelling idea called the RNA world hypothesis comes in. RNA, DNA's molecular cousin, is the star of this show. What's special about RNA is that it can do both jobs. It can store genetic information like DNA, and it can also act as an enzyme to catalyze chemical reactions, like a protein. So, in this early RNA world, RNA molecules could have both stored the recipe for life and built it. They could have been self-replicating, evolving and becoming more complex over time. Eventually, this simpler RNA-based life might have evolved to use the more stable DNA for storing information and the more versatile proteins for doing work, leading to the kind of life we see today. The RNA world hypothesis is one of the most widely supported ideas for bridging the gap between simple chemistry and a living cell. We have found evidence that RNA is an ancient molecule, and scientists have even created self-replicating RNA systems in the lab. However, a big question remains. Where did the first RNA molecules come from? They are complex, and their spontaneous formation on early Earth is still a major hurdle for this theory. So, where does that leave us? We have a collection of fascinating, plausible, and scientifically grounded theories. The primordial soup, the deep-sea vents, the clay templates, the delivery from space, the RNA world, each has its strengths and its weaknesses. Each has passionate advocates and critical skeptics. The truth might not be one single theory. It could be a combination of several. Perhaps organic molecules were delivered by comets into warm little ponds lined with catalytic clay, where RNA-based systems began to form, all powered by the sun and lightning. The puzzle is so complex that it is likely many factors had to align perfectly for the magic to happen. What's so exciting is that this isn't just a historical question. It's an active, ongoing field of scientific research. Astrobiologists are searching for signs of life on Mars and on the moons of Jupiter and Saturn, like Europa and Enceladus, which have liquid water oceans beneath their icy shells. If we find life there, even simple microbial life, it would be one of the most profound discoveries in human history. And if that life has a different chemical basis than ours, it would suggest that life can arise in multiple ways. If it shares our DNA-based structure, it might lend support to the panspermia theory, suggesting we have a shared origin. Back on Earth, chemists are in their labs, trying to create life from scratch. To understand the precise sequence of steps that can turn non-living matter into something that lives, breathes, and reproduces. Every new experiment, every new discovery, adds another piece to this grand puzzle. The fact that we don't have the answer yet isn't a failure of science. It's what makes science so thrilling. It's a testament to the sheer complexity and wonder of the natural world. It reminds us that there are still great mysteries out there waiting to be solved. The origin of life is a story that's still being written, and we are living in a time where we might just be able to write the next chapter. So the next time you look at a tree, a bird, or even your own reflection, take a moment to appreciate the mystery. We are all part of an unbroken chain of life stretching back nearly 4 billion years. To a single, mysterious origin event that we are still striving to understand. Thank you so much for joining me on this journey into one of science's greatest unsolved mysteries. If you found this fascinating, please hit that like button and subscribe for more deep dives into the world of science. And let me know in the comments which origin theory you find most compelling. See you next time.